Welcome to this session on the Schild plot, a fundamental tool in pharmacology. The Schild plot helps us quantify competitive drug antagonism, providing a clear way to measure how one drug can block the effects of another. This concept is a cornerstone of receptor pharmacology, shaping how we understand drug-receptor interactions and design better therapeutics. On the right, you can see an example of a Schild plot, which we'll explore in detail shortly. The origins of the Schild plot go back to 1947, when Heinz Otto Schild introduced the concept of PA in his landmark paper. Schild defined PAX as the negative logarithm of the concentration of antagonist that produces an X-fold shift in the agonist dose-response curve. The term PAX is analogous to pH in acid-base chemistry. Both represent negative logarithms of concentrations, making large numerical ranges easier to interpret. Today, we routinely use Pa2 values to quantify antagonist potency. This is the negative log of the concentration of antagonist that doubles the agonist dose or concentration required to achieve the same effect. To understand this, we use the concept of the dose ratio, the ratio of agonist concentrations needed to produce the same response in the presence and absence of antagonist. Mathematically, the dose ratio is expressed as the agonist concentration with antagonist divided by the concentration without antagonist. On the right, to visualize this concept, two dose-response curves for the agonist are shown. The blue curve represents the agonist alone, and the pink curve shows the agonist with antagonist. A horizontal line drawn halfway up the curves intersects them at different agonist concentrations. Dropping vertical lines from these intersection points gives the concentrations corresponding to equal responses. These concepts laid the foundation for the Schild plot, which uses dose ratios to quantify competitive antagonism with precision. To really understand how to quantify antagonism, we need to look at what's happening at the receptor level. This brings us to the receptor occupancy theory, one of the foundations of receptor pharmacology. The basic idea is that a drug's effect depends on how many receptors it occupies. The more receptors an agonist binds to, the greater the response, up to a maximum when all receptors are occupied. We can represent this with a simple reversible reaction. Agonist A plus receptor R interact to form the agonist-receptor complex AR, which then produces a response. This process is dynamic. The complex forms and dissociates continuously at rates determined by the dissociation constant Ka. Now let's consider what happens when a competitive antagonist B is added. The antagonist competes for the same receptor binding site to form an antagonist-receptor complex BR, which does not produce a response. This interaction is also dynamic, forming and dissociating continuously according to its own dissociation constant Kb. As a result, the total receptor population, R total, is now divided among free receptors, agonist-bound receptors, and antagonist-bound receptors. When a competitive antagonist is present, fewer receptors are available for the agonist, so a higher agonist concentration is required to produce the same effect, which is exactly what the dose ratio quantifies. The measured response is proportional to the fraction of receptors occupied by the agonist, relative to the total receptor concentration, including those bound to antagonist. At equilibrium, the proportion of receptors occupied by the agonist depends on the agonist concentration, its affinity for the receptor, and how much antagonist is competing for those same sites. All of this behaviour, the binding, the competition and the equilibrium, follows predictable chemical rules. Those rules come from a fundamental principle of chemistry known as the law of mass action, and that's what we'll look at next. The law of mass action states that the rate of a chemical reaction is directly proportional to the concentrations of the reactants involved. In pharmacology, this principle helps us understand how drugs interact with receptors. Let's begin with the simplest case, an agonist interacting reversibly with its receptor. According to the law of mass action, the forward reaction proceeds at a rate proportional to the concentration of agonist times the concentration of receptors, multiplied by a constant shown here as K4, the forward rate constant. The reverse reaction occurs at a rate proportional to the concentration of agonist bound receptors multiplied by the reverse rate constant Krev. At equilibrium, there is no net change in the concentration of bound receptors, so the forward rate equals the reverse rate. Rearranging this equation shows that the concentration of agonist bound receptors, which generate the response, equals the forward rate constant divided by the reverse rate constant multiplied by the agonist concentration and the receptor concentration. The ratio of these rate constants is related to the dissociation constant Ka, which is defined as the reverse rate constant divided by the forward rate constant. It is therefore the reciprocal of the ratio in our equation. Substituting this in, we get the concentration of agonist receptor complexes equals the concentration of agonist multiplied by the concentration of receptors divided by Ka. And the same principle applies to an antagonist B binding to the same receptor. So the concentration of antagonist receptor complexes equals the concentration of antagonist multiplied by the concentration of receptors divided by Kb. We can now use these equations to derive the Schild equation. It's the agonist receptor complex that generates the response, and we now know how its concentration is defined when the agonist is the only drug present. The next step is to see how this changes when a competitive antagonist is also present. The equation defining the total receptor pool brings the agonist and antagonist together. The terms representing the agonist-bound and antagonist-bound receptors can be replaced using the relationships we just derived from the law of mass action. This gives the total receptor concentration equal to the sum of three parts: the concentration of free receptors plus agonist times free receptors divided by Ka plus antagonist times free receptors divided by Kb. After factoring out the free receptor concentration R, R total equals the free receptor concentration multiplied by 1 plus agonist concentration over Ka plus antagonist concentration over Kb. Rearranging this defines the free receptor concentration as the total receptor concentration divided by 1 plus agonist concentration over Ka plus antagonist concentration over Kb. We now have a clear expression for the free receptor concentration in the presence of both an agonist and antagonist. Substituting this back into the equation for the agonist bound receptors gives their concentration when the antagonist is present along with the agonist. If we remove the antagonist terms, we recover the expression for agonist bound receptors when the antagonist is absent, but in the same format. When the agonist produces the same response in both conditions, these two equations are equal. The only difference is the agonist concentration needed to reach that response. So we'll label the agonist concentration in the presence of antagonist as A star. The ratio of the A star concentration to A is the dose ratio, the quantitative measure of how much more agonist is needed in the presence of antagonist. We'll carry this equality forward to the next slide, where we'll use it to derive the Schild equation. The first thing we do is cancel the total receptor concentration from both sides of the equation, since it appears in the numerator of each expression. Next, we multiply both sides by each of the denominators. This step clears the fractions and gives us a simpler equation to work with. We can now cancel the common agonist dissociation constant because it appears on both sides of the equation. After rearranging the terms, the equation now reads like this. The agonist concentration with antagonist plus the product of agonist concentrations with and without antagonist divided by the agonist dissociation constant equals the agonist concentration without antagonist plus that same product term and an extra term for the antagonist. The product of the agonist and antagonist concentrations divided by the antagonist's dissociation constant. The common fractions cancel out. Then, dividing both sides of the equation by the agonist concentration in the absence of antagonist leaves us with a simple ratio. The agonist concentration with antagonist divided by the agonist concentration without antagonist equals 1 plus the antagonist concentration divided by its dissociation constant. As you've seen before, the ratio of agonist concentrations with and without antagonist is the dose ratio, usually written as R. Now we have an expression that defines the dose ratio entirely in terms of the antagonist. From here, we subtract 1 from both sides, giving R minus 1 equals the antagonist concentration divided by its dissociation constant. Finally, we take logarithms of both sides, and that gives us the Schild equation. If we compare this with the familiar straight line equation, y equals mx plus c, the similarity is clear. The slope m is equal to 1, and the intercept gives us the antagonist's affinity. So let's now look at how this relationship appears as a graph, the Schild plot. On the y-axis, we plot the logarithm of the dose ratio minus 1, and on the x-axis, we plot the logarithm of the antagonist concentration. Data that follow this equation will form a straight line with a slope of 1. In summary, the Schild plot provides a quantitative way to assess antagonist potency and mechanism. It allows us to quantify competitive antagonism and estimate antagonist affinity through the PA2 value. A linear plot with a slope of 1 confirms competitive antagonism, but when the slope deviates or the line curves, it reminds us that real receptor systems can behave in more complex ways. The method has limitations. It assumes equilibrium, a simple receptor model, and requires accurate measurements across several antagonist concentrations. So, while the Schild plot is powerful, interpretation must always consider the biological context and experimental design. Thank you for joining this session. If there are topics you'd like to see covered in future videos, whether it's related to receptor pharmacology or something else, please share your suggestions. Your ideas help shape the next set of resources.